Welcome to Dr. Vanderbilt's Basic Chemistry Podcast. Tonight we're talking about resonance. Our objectives for this podcast are to define the term resonance and draw some resonance structures so you can actually see what we mean by this definition and so you can recognize these situations. You may have noticed, or you will shortly encounter, situations where it's possible to draw more than one correct Lewis structure for a given molecule or polyatomic ion, where the set of correct structures all share the same basic skeleton. They have the same numbers and types of atoms and the same spatial arrangement in terms of who's bonded to whom. So we're talking about the same molecule here. And within this set, they all have the same numbers and types of bonds. So they have the same number of single and double bonds. But there's more than one possible location for those double bonds. And so we can get a little tricky. One example of a molecule for which this is true is the ozone molecule, which has 18 valence electrons. Now we can draw the ozone molecule as 3 oxygen atoms in a row. And when we start assigning electrons, we end up with 1 double bond and 1 single bond. So in this molecule, I've chosen to draw the double bond on the left. We can put in the rest of our lone pair electrons. And this is a perfectly correct Lewis structure. However, I could also draw the double bond on the right. And I can go ahead and put all my lone pair electrons in.
So I leave it turned off.
And this is also an equally correct structure. There's no reason to favor one of them over the other. They're equivalent. Yes, the location of the double bond is in different places, but except for that, they are completely equivalent. These are resonance structures, and when we draw resonance structures, we separate them by a double-sided arrow. We're trying to say that the true situation is somewhere in between. I'd like to explain that with an analogy. One analogy for resonance is using color. If we were to mix blue paint with yellow paint, we will get a green paint. The green paint is its own identity. It is its own color. We made it from blue and yellow, but we have this intermediate case in between. We have a similar thing going on with resonance. We have this resonance structure of ozone. We have the second resonance structure of ozone. The true ozone molecule is something in between. It's not blue, and it's not yellow. It's a blend of which is green. That's really what we're trying to get at here. All right, so the true structure is a blend of the two original Lewis dot diagrams. It's something in between. It's not one or the other, and it's not flip-flopping back and forth. The true structure is some intermediate state, or some intermediate structure. I've actually seen Lewis diagrams for ozone where it sort of shows half a bond all the way around, trying to indicate better what's going on. All right, but you can't really adequately draw the true state of ozone and explain what's going on using Lewis diagrams because they are limited, because they focus on pairs. Right? They do require localized electrons and pairs of electrons, as I just said. Right? And so that can make resonance structures a little hard to do. What we're sort of doing is capturing two extremes, and the real picture is somewhere in the middle. Occasionally you will find when you are drawing Lewis structures, you can put together non-equivalent Lewis structures where they don't have the same numbers and types of bonds in the structures. And in order to evaluate those, we'll have to use formal charge, which is beyond the scope of this podcast. But I'll have a separate podcast shortly to help you talk about formal charge. So just leave that to the side for the moment. Benzene is a molecule that is a classic example of resonance. In fact, if you only knew one resonance structure, it would be benzene. Now, benzene has the chemical formula C6H6. It's a six-membered ring for the carbons. And then the hydrogens are outside of that. So let me see how neatly I can draw a six-membered ring. All right, where the two lines meet would be a carbon, so that's six carbons. And then the hydrogens are hanging off. All right, but if you count valence electrons, and there would be 10, all right, we end up with alternating single-double bonds. But we could, of course, draw a different structure, which is equivalent, where the double bonds are in different locations. All right, and that's what we're trying to show down here. All right, these are classic resonance structures of carbon, where the double bonds appear to be back and forth. The truth is, the double bonds are not flip-flopping locations. It's sort of more like 1.5 bonds all the way around. And the electrons really aren't localized as to belonging to this pair of carbons or belonging to that bond. So a lot of times you'll see chemists will draw this structure for benzene, which is emphasizing the fact that some of those electrons are being shared by the whole molecule. But we can't adequately draw this with a Lewis structure. We need other bonding theories to do that. So in Lewis diagrams, really what we're doing is trying to say that we've got a situation we can't quite explain, here's our best way to draw it.